All right, well, it is start time, so we will begin. Probably don't need to remind you, but I will nonetheless. Where are we? Well, we're going to get started here with chapter 25. I know the syllabus had us starting chapter 24. You might remember on Tuesday that I got wrapped up in doing a bunch of problems and illustrations on how to calculate Gauss's law. I think it was time well spent, don't get me wrong here, but it has put us a little behind the schedule, if you will, a little pressure to make sure we get started and through this. Fortunately, it's not that long of a chapter, but nonetheless, I still would like to do examples for you, which I don't think we will have time. So the goal here today is to talk about the material that's in there, and then we come back on Tuesday, do some more examples for you. So this weekend, do the problems at least the best you can to the best of your ability, with the idea that, remembering on Tuesday, you don't necessarily need to turn them in, that I'm going to do some more examples, some more calculations, and then that, of course, means you can turn them in on Thursday. But we better not fall any further behind here, because we've kind of used up what I call my buffer space before that next exam. So now we need to kind of stay here on task. Which kind of reminds me, I see a little bit of a pile up here, and that's good. I would expect many of you also have chapter 24 that you haven't turned in, because I did get a stack, and judged on its size, I would guess that more than half, but not nearly quite all, turned it in already in 24. So this isn't going to make that much of a difference. So it tells me a lot of you still have it, and you're ready to finish that up and get started. So what is chapter 25? Well, it's our third chapter. It is another way to find the electric field, but it is even more than that. So we kind of expand beyond just what we've learned so far in these first 2 weeks here. Let me see if this picture helps. You've seen it a lot. I like to put this picture. I think it's a good diagram illustrating of kind of the logic one would use to solve problems. The first time you saw it was kind of back, and actually, I'm going to lower it down a little bit so I can have some room above it. But the first time you kind of saw this diagram was in Physics 121, and I think I've used it again already this semester. But this was our fundamental mechanics, that position, velocity, acceleration, they're all related. You know that you take derivatives and integrals to go back and forth between one and the other. And of course, then this is chapters 1 through 4 of the book. Then chapters 5 and 6 dealt with Newton's laws, so we dealt with forces. Now in Physics 121, I kind of put net force and then the sum of the forces. I'll just put net force, and for this class, then we can say that net force comes from the sum of the electric field, or it comes from Gauss's law. And so I'll just put this E dot dA. And so if I was kind of describing to you, kind of highlighting in this diagram what we've done, I guess I would say here is where we got started. This is our chapter 23. This is what we learned first. This is Coulomb's law. We learned how to find the electric field from a single point. We talked about the concept of the electric field. But the big lesson is, once we knew the electric field from a single point, then you could find it to any shape, at least in theory, right? You could just say, well, what if it's a rod? What if it's a ring? What if it's a disc? What if it's a cylinder? And the whole idea is you would add it together. And maybe you would take a bunch of points to make a ring, a bunch of rings to make a disc, a bunch of discs to make a cylinder. Okay? And so we did problems like that. And so, just kind of jogging your memory there, we then went on into chapter 24 and introduced you to the idea of flux, and went through that hopefully the same logic that Gauss did, or at least pretty close to it, and said, look, when you look at Gauss's law, there's something about this flux. If you take a closed surface, and if the flux is not zero, then that means there's got to be charges trapped inside, and that was our argument there. And so we could use the idea of symmetry, we could use the idea of flux, and even though our charges configuration may be pretty complicated, often that simplified the problem to what we would call a flux integral, but the flux integral never really turned into be an actual integral. We usually pulled the electric field out. The trick was really the correct Gaussian surface. And so that's the chapter that I just did a bunch of examples for you. You just did a bunch of problems for. So now what are we going to do? Well, again, the idea is about electricity here. We haven't changed that. We soon will. We will, well, I guess we'll get a couple steps before we get there, but we'll eventually get to magnetism. But this idea here with Gauss's law was giving you two tools, if you will, to find the electric field. And of course, learning the concept of the electric field along the way. Let me also remind you, back into Physics 121, we did this part, which chapters 1 through 4, 5 and 6. Does anybody remember what we did in 7 and 8? What was the next thing we did after? Yeah, we got into those 3 conservational principles. And the first one was conservation of energy. And if you kind of remember the diagram, I put it up above here and I said, what was the advantage of conservation of energy? In other words, if I took this pin and I held it up above the table and I let it fall, could you tell me the speed right before it makes impact? Could you find that? And hopefully you remember you have 2 ways of getting there now, right? One way is to say, well, sure, I can look at the net force on it, right? I could look at the force of gravity and even air friction if I want to include that one. And the force of gravity would lead to the acceleration of gravity. The acceleration would lead to the velocity. Fair enough? But that wasn't the only way. We also talked about its energy. We said it had a gravitational potential energy. And as the object fell, it lost its gravitational potential energy. And what happened to it? Right, that was our conservation principle. Energy just didn't disappear. There was this conservation of energy that said that energy had to go somewhere, right? It had to go into a form of kinetic energy. And so that's how we got to velocity. And so our diagram was expanded at this point. Instead of being a nice linear line anymore, it's kind of becoming a complex web of how we might solve a problem. And of course, the problems got a lot harder at that point because it wasn't do this, do this, do this. It's, well, do this to here and then flip over to that. And then, you know, and so what you had to do to figure out the answer became more involved. In fact, it wasn't the only thing that energy gave us. Energy could have given us velocity, but if you remember us talking about taking the derivative of the energy, didn't it also give us forces? And so we could get the x component and the y component and the z component by taking the derivative of the energy. Now, I trust you haven't forgotten that because we're about to repeat it. Okay? And so just like we have been doing here, and we talked about forces, and we got 2 ways to get to forces which lead, we should now talk about the energy. See, if there was a force of gravity which led to a potential energy due to gravity, now in this class, if there's an electric force, then there should also be an electric potential energy, which we will also talk about another object of electric potential. And so my first warning here is we'll have both. We'll have an electric potential energy, which I think you can easily understand here. But we'll go one step further and talk about an electric potential. And that's something we didn't really quite do in our mechanics, in our gravity part of it. But we will here. And that is the title of this chapter here. This chapter is saying, let's look at an object called electric potential. And that's sort of my lead in. And just like we never really add up the total forces to get the net force, what we do is we add up the electric fields. It's better, it's simpler, it's certainly more fundamental that way. Once we have the electric field, we can get the force real easy. And we're going to see the same thing here. We probably won't deal too much with electric potential energy originally. What we will deal with is this thing that the chapter is going to introduce is the electric potential. The electric potential will lead to the electric potential energy. And then, of course, once I have the potential energy, I can then find the velocity or I can find the force. And just like these two differ by the charge, we'll see that these two differ by the charge. So when you took the derivative of energy and you got force, Now you're going to see when we take derivative of potential, we'll get electric field. And so that's what I alluded to last lecture, that, hey, this chapter is going to give us a third way to get to the electric field. And so, again, hopefully before today's over, I will show you a bunch of examples. And certainly not if today, definitely on Tuesday, of how I might get the electric field. But I hope I'll do one step better than that. It won't just be another way to get to the electric field. It will be an alternative way to get to the speed of the electron. So if I take something as simple as, say, this ring or this disk, which fortunately has a hole in it, and I take this disk and I say I charge it positive, and I take a little electron and I hold it about a meter away and I let it go, won't it be drawn to the disk? And in this case, go through the middle, or in the case of the ring, go through the middle. And so what is its speed when it gets right in the middle of that disk? Right? And so now I will have two ways of answering that. I will have, well, we can do the force. Now the reason I want to avoid that is we've already talked about the electric fields from this ring, right? Is the electric field a constant? So is the force a constant? So is the acceleration a constant? And weren't those the harder ones to figure out the speed where it kept changing? Right. But those problems became really easy to find the speed when we dealt with energy, right? Energy goes with position. Acceleration goes with time. So if you say, what is the electron after it moves a meter? Use energy. It'll be easy. And that's hopefully what you will remember and we will put together as we go into this chapter here. So, all of that, as you can see, is drawing your attention back to some of the stuff we did back in chapters 7 and 8. And in chapter 8, we had this. What was our definition of change in potential energy? And maybe I should start there. What was the symbol we used for potential energy? The U, right? All right, so there it is. So change in potential energy. How do we get the change in potential energy? Do you remember? Good. It was negative of an integral as we'd go from some initial point to some final point of the force taught the distance it moved. Fair enough? Now, if this was gravity, so let me come over here, because I don't want to focus too much on gravity anymore, but again, I don't want you to have forgotten what we did. We often did this. We said, let's look at the change in potential energy due to the force of gravity. And so when we did that, we put the integral, we put an initial, we put a final, we put the force due to gravity. We took a dot product, dr. If I draw a little picture here and say, okay, here is the ground, and I take an object here. I gotta do something other than baseball. The Dodgers are just killing me. All right? So good, it's a good time to study, because, I mean, first place, forget that. Wild card, oh, after last night, forget that, you know. 2 runs in 27 innings. My little leaguers can do that. Oh, sorry. All right. So something different than a baseball. Bicycle. I like riding my bike. All right. So a bicycle. I can't draw a bicycle very well. Baseballs are easy to draw. All right. All right. So there's an ugly looking bicycle. I better go back to the baseball. All right. All right. So here's this object. Okay. And so I'm going to take this object and you're going to lift it up. Okay. So this is the initial position. This is the final position, okay? So in our case, let's just say the initial position is height 0, the final position is then some height y, and so just again to jog your memory on what we did is we put in the negative, we put in the integral, we said from 0 to y, we looked at the force of gravity. The force of gravity, if we don't change too much, if you remember, we don't have to use Newton's universal law of gravity. We just have to use the mg. All right. So this is mg. It's in the j hat direction, or excuse me, negative j hat direction, right? Force of gravity is down. Okay. And then if I'm going to move it, in this case, my dr, I am moving up on the y-axis. And so when I do this integral, the negative cancels off, and I get mgy for the change in potential energy. I guess technically it's mgy minus 0 there if you want to put from y to 0. Again, not so much that I'm interested in repeating our mechanics. I do trust you haven't forgot it, however, but that's what we talked about energy. That's where it came from, right? It was an integral force dotted with distance. Fair enough? So let's do the same thing here, but now our force becomes the electrical force instead of the force of gravity. And so now we will be talking about an energy. We won't call it a gravitational potential energy, but we will call it an electric potential energy. And so in this chapter, chapter 25, I will start off and say the change in potential energy electric. And so we'll put a little subscript E to talk about the electric potential energy. In our mechanics class, we had gravitational potential energy. I guess we also had a spring potential energy. Remember the 1/2 kx squared? And again, let me not repeat that, but we used a subscript S for spring. We used a subscript G for gravity. Now we're going to use a subscript E for electric. And later on, we'll have magnetic. Although we'll use subscript B for that one, so we'll wait. We'll wait there. It won't be M for magnetic. It'll be B for magnetic. All right. And then now we will put in then our force electric dotted with dr from some initial to some final. Okay, and so that's the fundamental idea, right? Except we will go one step further. This is really potential energy. We will go a bit further. For the same reason, back in the last 2 chapters, we didn't focus too much on the force, we focused on the electric field. Right, so let me repeat what I had said, and then add to it here. If I took a sheet and I charge it up positively, and a second one negatively, just to kind of review here, what would the electric field look like from 2 sheets, one positive, one negative, equal amounts? We did this one on Tuesday. Important one, we're going to see it a lot, so what does it look like? Do you remember? Okay. Yeah, this is the one, and maybe I'll switch to a blue for the electric field or something here. But this would create an electric field in the inner space between them that was nice and uniform. Okay? That is an important lesson to learn. And in fact, I have 2 plates right here. I will charge them up. Unfortunately, I don't have a little electron to move back and forth. We'll do something similar to that in the lab. But it makes a good show and tell. Here's 2 parallel plates. I can put a positive and negative. And so here is my electric field. Now, just to get a quick review, do you remember the equation for the electric field between those 2 plates? Based upon how much charge I have. What was it? Sigma over epsilon naught. Right? What was sigma? Charge density on the plate. What was epsilon naught? Permittivity of free space. Its value? 8.85 times 10 to the minus 12. Notice there's no 2 in there. Why not a 2? 2 plates, right? They added together. How about outside the plates? What's the field? 0. Okay, so don't forget that. So here I'm just going to draw what the electric field looks like from 2 parallel plates. And I'm going to ask this question. What if I come along and put a charge right here? Which way's the force? You can't answer that, right? Because you don't know what kind of charge it is. Fair enough? Because a positive charge would go which way? To the right. You're right. Which way would a negative go? Right? To the left. And so our lesson here in these last chapters was that when you go to look at the force is the charge that you place there times the electric field. And so if the charge you place there has a negative sign in it, the force is the negative of the direction of the field. Now, notice the direction of the field had nothing to do with what charge I placed there. Fair enough? That's why I was trying to say it's much nicer and much easier and something more fundamental if we study what is the field and not is the force. Because we really don't know what the force is. In fact, there's not even a force until you put another charge there. But the field, we can talk about a field. We can talk about this change in the space or between the plates, even if there's not a second charge there. And if there is a second charge, we don't have to care whether it's positive or negative. And so we cared more about the field than we did the force. Now, don't get me wrong. Ultimately, the field leads to the force, which leads to the acceleration, which leads to the velocity, which leads to the new position of this charge. That's ultimately what we're going to care about. What's going to happen to this charge? Where is it going to go? But as far as the education, as far as the fundamental physics, as far as the calculation, what I've got to get you to learn is how would I calculate the field? That's why we focused on the field, right? Fair enough? All right, now let's expand that into this chapter. If I were to look at that situation and look at the change in potential energy of this charge as it moved, do you see a problem I run into? Which way's the force? Depends what kind of charge it is, right? So let's get away from that. Let's get away from being dependent on what charge you put there. So just like we got away from the force and we went to electric field, that allowed us to be separate and to look at the physics of what's going on without worrying about what the sign of the other charge is. So that is why we won't spend too much time talking about the energy in the same way we didn't spend too much time dealing with the force. We went one step back, if you will, in the fundamentals. We went to find the electric field. And I'm going to say the same thing here. Notice the pattern. We're going to go one step back. We're not going to be talking so much about the potential energy. Now, don't get me wrong. Will we need the potential energy? Oh, absolutely. But one step back of that leads to something you haven't seen before called electric potential. Electric potential, then, is something I can call, it's related to the electric potential energy. Boy, they sound the same, right? Electric potential energy, right? But they're not. What's the difference? What do you think I'm going to do? What if you were to divide by charge? How would you calculate the force? Wouldn't the force be charge times the electric field? And so, if I may clear the board over here on the side, this is where the chapter begins. The definition of electric potential. And hopefully, by me presenting it this way, you'll see the value of the electric potential. What I'm going to do then is say the change in electric potential energy per charge is negative. And maybe I'll do this in two steps. Here's my integral, initial to final. And in place of electric field, I will put charge times electric field, dr. But since I'm dividing by Q, look what happens. The Q cancels out. And what we have then is an integral not of the force, but an integral of the electric field. Okay? And so we are going to call this then its electric potential. So the electric potential, if you can see in here, is related, but not quite the same as the electric potential energy. What it is if you take the electric potential energy and you divide it by its charge. In other words, electric potential energy is not the same as the electric... Wait, so I'll try that again. The electric potential is not quite the same as the electric potential energy. Related? Yes. If you know one, do you know the other? Yes. You're just going to have to multiply by charge. Just like we did before. We will focus on the electric field. We will add a bunch of electric fields. If you know the total electric field, could you get the force? Yeah, you would then multiply by charge. So it's a very simple step to go from field to force. And same thing here. It's going to be a very simple step to go from potential to energy. All you got to do is take how much charge you're going to place there. But notice then the potential is well defined. It does not matter what charge you place there. So when I look at something like this, and I say, I'm going to put a charge Q and ask you which way is the field, fact that you knew this plate was positive and this one was negative, you know the field's that way. But if I were to ask you what way the force is, that's where you say, I don't know. I cannot tell you which way the force is because it depends on the charge. Fair enough? And I'm going to end up saying the same thing. If you put a charge Q here, is this way lower potential energy or is it this way lower potential energy? Don't know because I can't tell you which way is lower energy because I can't tell you which way the force is. But I can tell you what direction the electric field is. And if I can tell you what direction the electric field is, I can tell you what direction is an increase or decrease in potential. Okay? And so don't mix that. So the potential is what really going to be much more useful to us. The potential is well defined. The potential energy depends. Well, do I have an electron or do I have a proton? You know, which way is it moving? So that's why we're going to deal with electric potential. So keep that in mind, that electric potential is very closely related to electric potential energy. If we spend this whole chapter teaching you how to calculate electric potential, then I'm hoping you can continue the next step. Could you get electric potential energy? Yeah, you just multiply by charge. And then if you knew electric potential energy, could you get velocity? Yeah, I would use the principle of conservation of energy. I would say, what is the energy before I let the electron go? It moves. What is the energy after? Include potential energy, electric potential energy. And any other energies we might have. Usually the electrons are so small that we probably won't include gravitational potential energy. We probably won't include any springs. They won't be lying around there. But they will be moving fast, so we will include kinetic energies. And that's how we'll find out how fast is it going. Okay? And so that's the big picture I'm trying to get across here. That's what this chapter is about, right here. Chapter 25. Let's find this. How do I get electric potential? And why do I care about it? You know? And that's why I care about it. It'll give me velocity. It'll also give me electric fields here. All right? So let's look a little closely at some symbols. This side of the equation, we've already used change in potential energy. You've seen. We've already used charge Q. And I haven't given you the symbol yet here, but I think you know it because you all read this chapter either last night or the night before. So some of you are smiling, so good. That's true. That's you looking away. What does that mean? All right? And so those of you who did look through here, what's the symbol that the book has chosen and kind of the universal symbol for electric potential? It's the capital V. Mm-hmm. And so we will go V. Okay? And we should talk about the units. Since this is the new quantity, electric potential, that's why I wanted to spend so much time of explaining what it is and why we care about it. You know? So what are the units? Yeah, you see it right there? It's joules per coulomb. So again, that's why I said electric potential is not energy. It's not so many joules. It's how many joules per coulomb. Okay? And so it's a useful number in the sense that it can give me the overall energy once I multiply it by charge. Just like the signs at the gas station. I mean, I got in my car this morning and I go, oh man, I better stop to get gas before I drive away. And it's like, okay, there's a gas station on that corner and it said 425, and there's one on that corner, it said 415. And I was like, does that mean I can go in there and fill up my whole tank for 415? Because I'd like that. That's not what the sign meant, 415, is it? What did the 415 mean? Price per gallon. And this is the same thing. This is not really telling me, when you tell me the potential, you're not really telling me the total energy it has, are you? You're telling me the energy it has per charge. And so really, to figure out how much I had to pay when I got gas, it was, 415 times like 16 gallons I got, and so, whatever that multiplied out. Good thing I didn't have to look. You just swipe your car and walk away, right? And don't look at the tank there. But that's the total cost. And I'm trying to say the same thing. That'll give you, hopefully, some insight to electric potential. In fact, like we do so often, we don't just leave it as joules per coulomb. we give it a name in honor of the great scientists working in the field. And so what do we call this? Yeah, we call this a volt. Symbol capital V also. Be careful here. What's the symbol for the quantity of electric potential? V. What's the symbol for the unit to measure electric potential? V for volts. And I think that, I would think that would be the least confusion, but it's not. It's the most. I mean, when we did mechanics and we said the distance is 10 meters. For the quantity distance, we used D, or in this class we were more mathematical, so we did X. And so we used the quantity symbol X, we used units in meters. If we did mass, we said the mass is 10 grams, right? The symbol for the unit was different than the quantity. Now we're going to go, the electric potential is 10 volts. Ooh. Don't mix those V's. So we use the V for the quantity, but we also use the V for the unit. Okay? So keep that in mind. I think that's why so many people, when they say, they read the book and the book says, solve for the electric potential. And they ask me, what am I looking for? Oh, well, the V. Oh, I'm looking for the voltage. Well, yeah, it's measured in volts. And you can call it voltage or you can call it electric potential, but you're not looking for the volts. Right? You're looking for the quantity. You're looking for the voltage. You're looking for the electric potential. It's measured in units of volts. Fair enough? Well, maybe I'll spend too much time there, but I think you got that idea there. And so remember this, that voltage is saying how much energy per charge. So, I'll give an example here. These plugs that you see around your house. We haven't done much with these plugs, but does anybody know how we label them? They've got a certain voltage, don't they? A certain electric potential. What is it? Yeah, we like to say they're 120 volts. Well, what do we mean exactly by that? If I plug in my lamp and turn it on and the light goes off, I'm plugging to 120 volts. Meaning, what do I mean by that? What that means is electrons are coming out of that wall. They're going through my lamp. And every single electron has a certain amount of energy, the same amount. What if 6 billion electrons go through my light bulb? Now maybe I better pause there. How much charge is 6 billion electrons? That was the 1 Coulomb we did a couple weeks ago, right? All right, so if 1 Coulomb, if 6 billion electrons go through my little light, how much charge is that? 1 Coulomb. How much energy is that? 120 joules. So what did I mean by 120 volts? I get 120 joules for every Coulomb of charge. Okay? That's the concept, the conceptual side of this math, of this equation. Watch, I bothered to grab some batteries here. Here is a battery you probably are familiar with in its size. We call it a D cell. This is also a D cell. This one's cut in parts so that the students can actually see the chemicals inside. There's the zinc on the outside and the copper on the inside. So there's my zinc copper battery. Again, it's a D cell. All right, here's another one. This is a double A. Here's a little smaller one. Here's a triple A. Coming up, we'll work more with batteries, but anybody know the voltage on, say, this bigger one? 1.5 volts. It says 1.5 volts right there. 1.5 volts. Okay. Well, let's compare it to the small one. Here's my double A. What's the voltage on this one? 1.5 volts. It's smaller. How could this possibly have the same amount of energy as that one? It doesn't, does it? It has the same what? Same electric potential, right? The same voltage. Don't say the same volt, right? But it has the same voltage. It has a measure of 1.5 volts. And so again, just like that gas station, I pulled in to the gas station. It was 4:15. I filled up my little car, and this RV pulled in. Did we pay the same amount? Had an empty tank, filled the whole thing up. I think it was $220 or something ridiculous thing, right? Filling up that tank, right? All 80 or so many gallons, right? Did we pay the same price? No. How come his cost so much more than mine? I thought we were each paying $4.15 per gallon. What does this mean? 1.5 volts? Same energy per charge. But coming back to this, you can see the charges is coming from a chemical reaction in here. So, do these have the same amount of charge in them? No, this is going to have a lot more chemicals in it. And so even though these have the same energy per charge, this has a lot more charges and hence a lot more energy. So no, these do not have the same energy. This is great. This is what I put in my calculator. This is what I put in my little racing RV car. This just wouldn't cut it. There's just not enough energy. I'd put it out there, in 30 seconds it's dead. This, I'll get about 20 minutes out of it, right? And so there's a lot more energy in here. And so same thing here. Anybody know the voltage on these AAAs? 1.5 volts also, right? They're all the same amount of energy per charge. The difference between those is how much charge we have. Here's a battery you probably haven't seen. This is our laboratory one. But when we cut it in half, it's still copper and zinc. So what's the voltage? It's 1.5 volts. It's still the same per charge. But it's a very large battery with a lot of charge in it, and then hopefully will last a very long time. Although, I guess we've kind of gotten away from batteries, so we won't have those in the lab anymore. We tend to have some other power supplies, as you'll see there. But again, I'm hoping that illustrates what, again, I'm trying to get across here, that subtlety difference between the electric potential and the electric potential energy. So I'll say it again. Here's what I'm going to do. I'm going to spend the chapter trying to teach you how to calculate this, electric potential. Because once we know this, then we can quickly multiply by the charge to get the energy. Once I get the energy, I can then do conservation of energy and get the velocity, okay? Or the other way around, if I know the potential, I can take its derivative and get the electric field. So the real key here is, what is the electric potential, say from a point charge? Because if I know it from a point charge, can't I just add a bunch of point charges and get a ring, a disc, a cylinder, a rod, right? And I can get any charges I want. So we're going to use our same calculus that we already saw back in chapter 3. Add up a bunch of point charges. Well, I'm sorry, I'm trying to get ahead of myself here. So let's come back to this plate here. Let me use this simple electric field as kind of my first simple example. Yeah.
So if you have a battery that is a different voltage, does that just mean that you'll knock off more energy
Per charge. Or per single reaction, you might say.
I'm trying to visualize that. So would it like give energy faster, or?
Not necessarily faster, just it has more energy when it reacts. If you maybe if you're on a microscopic level in this chemical reaction, it's a redox reaction, half of it is sending an electron out. Well, it would send it out with more force as that electron comes in. A lithium ion, very popular one that you guys all have in your cell phones. But they're 3 volts. That's why they're there. You get a lot of energy per one chemical reaction. About twice as much as these. And so that's why you have all these lithium ion batteries. Plus they're rechargeable and hold a decent charge and a lot of other good reasons here. Okay? But that's what voltage means, right? How much are you getting in that single reaction, if you will, that one chemical reaction, sending that electron. But that, I guess I shouldn't even say that. That's half the reaction. But, you know, it's a combination of when it reacts, the electron's got to get kicked out. Then the other half has got to suck it in. So between the redox part of it, we got to get the whole thing. Okay. Well, let's retry this. Because now that we've got at least the fundamental idea down, let me start right here. Okay? Let me put this equation over here next to my first configuration and say this. That if I take negative an integral from some initial to some final point of E dot dr, that would then be the change in potential. Okay? And so now let me actually use this symbol. So I'm going to take this symbol, put it there, look at this equation. All right? Now the reason I want to look at this one first, like I said, it's probably the simplest one, because you just told me that the electric field from a parallel plate is nice and uniform, right? So if I were to, and I'll go back to the red here, maybe I'll forget about the charge there. That's the neat thing about talking about the potential. It has to do with the field. There doesn't have to be another charge placed there. If doubt there is, then there's a force and then there's energy associated with that charge. But without that charge there still is a field but not a force. There still is a potential but not a potential energy. Okay? Well, let's go ahead and say we move from one point to another. Why don't I start, say, right here. I'll call this the initial position. I'll move along, and I'll go to my final position. Okay? And so I'll just be internal to this parallel plate. I could go the whole distance. I could go from one plate all the way to the other and find out what is the change in potential all the way from one plate to another. Or I could just be a subpart of it. And it doesn't really matter what I am. And so I'm just going to do a little subpart here and say, all right, I will start here at what you might call X initial. And I will finish here what I will call X final. And let's just do this integral, okay? And so this integral, not the most exciting one in the world, but it hopefully sets up this pattern here, is I would put a negative. I would say, okay, I'm going to start at my initial position. I'm going to go to my final position. And I would say, all right, what is the electric field? Now, assuming I already have done the past chapter and I've done Gauss's law, I know the electric field. You told it to me earlier, so I'm going to put that. The electric field is sigma over epsilon. But it has a direction. What direction is it? And of course, in this picture, right, it's to the right. So I'd put a little I hat, if you will. What direction am I talking about moving? Well, I guess I'm moving with the field. I'm moving along the x direction, and so that would be a little movement in the x direction, and the direction would be I hat. Okay? Now I want you to notice something here. That if I move in the same direction, or since it's a dot product, if I move in somewhat the same direction. In other words, this has a cosine of the angle, right? But if that angle is less than 90 degrees, isn't cosine of some angle less than 90 degrees a positive number? And so what I'm saying here is I add this up, plus, 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 they would all be positive. And so what am I going to get here for my total answer at the end? Negative, right? So as I move from initial to final, my question for you is, does the potential change? Does it increase or decrease? Decrease, right? So when you are going with the field, you would be going to lower potentials. If I was going the other way, against the field, what would be happening? Increasing in potential. This dot product here would be an angle greater than 90 degrees, giving me a negative, coupled with that negative, giving me a positive. So again, there may not be any charge here, but if I were to tell you this, that if I were to tell you, I'm going to put my finger here at initial and move it to final, could you tell me if the potential increased or decreased? Yeah. And it decreased, didn't it? The electric potential is decreasing as we go in the same direction as the field. Increasing as we go against the field. What about the potential energy? When I go from here to here, did the potential energy increase or decrease? Can't answer that until I put a charge there. Thank you very much. That's the point, right? This equation that was over there would say the change in potential energy is charge times the change in electric potential. So again, the nice thing about working with electric potential and not electric potential energy is the issue of what kind of charge you place there is gone. Just like electric field and forces. Okay? So, why don't I do this? Why don't I say, I'm going to put a negative right here. You already told me earlier, if I put a negative there, which way will it go? Won't it go over here to the left? So in terms of change in potential, this negative goes which way? To higher potential or to lower potential? Doesn't it go to higher potential? How about a positive charge? Which way would it go? Lower potentials. But now let's look at the energy. Let's look at this electron. You just told me that it's moving here to higher potentials. Its change in potential is positive. But what is its change in potential energy? Isn't it negative? Why? Because Q is negative. So as this electron moves to our left, it is going to higher potential but lower potential energy. How about the positive one? Which way does the positive one move? To the right. That's lower potential, right? How about energy? If I put a positive charge here and I move to lower potential, that one's negative, that one's positive, what do I get here? Negative, lower potential energy. Do you catch that? Did you catch that the negative moved to lower potential energies and the positive one moved to lower potential energies? Didn't we have this discussion in mechanics that if you put something up here, the reason it falls is because it's going to go to lower potential energies? Did you see how each one went to lower potential energies? It was just a different direction. That's why we don't really want to talk about the value of the electric potential energy, because it depends on what charge you place there. So don't forget that yes, they each are moving. Yes, they each are moving to lower potential energy. But the potential, not the energy, the electric potential is lower this way, higher that way. Okay? And that will be helpful. We can well define what the electric potential is. We can't well define the electric potential energy because then it depends on what charge you place there. Okay? But I would say that they both moved to lower potential energies. It's the electron, though, that goes to higher potentials, which is lower potential energy for it. The positive one moves to lower potentials, which is lower potential energy for it. Whew. Does that make sense? All right, well, I hope it does, because that's exactly what you're going to be working with here in terms of the math. All right, well, I'll keep going here, because again, the point here is to get you that gut feeling for electric potential, to illustrate what it is and why we're working with it and why it would be better than the electric potential energies. And here it's well defined. Just like the electric field is well defined, the electric potential is well defined. Now if I actually do this integral, I will get, let's see, I can pull out my constants, sigma over epsilon. My dot product, I hat and I hat, that's just 1. So then I get an integral of a dx, which is just x, so that would be x initial. Then I would have a negative in front. Fair enough? And so there would be my equation for the change in potential. If we kind of generalize it, we might say this. We might say, pick a reference point, maybe this plate right here, and we will say one of the plates is 0. Usually we like to call the lower one 0, so maybe I should call that one 0. But either one we can call 0 here. But you can kind of see the equation then for the electric potential from this parallel plate is this. And so there's our first equation for electric potential. A very simple parallel plate. It's an integral. Okay? I must admit we don't use it much for potentials, probably because the electric field is so simple there that we can do all of our stuff with constant fields, constant forces, constant accelerations. So the other ones that I'm about to show you really are where we're going to focus our attention. But I like it because it does give me the first step of my illustration. I'll erase this now, but keep this little diagram in your head. Actually, maybe I'll leave it there and just start working underneath it. But the whole point of dealing with this was to ask, could you get the velocity of something? Let's give it a try here. Let's go ahead and actually then say, and maybe I'll pick one. Why don't I pick the negative one? Let's actually say that I put a negative right in the center. Okay? And so there's my charge Q, right in the center. Now, so I have a number to work with. Let's say that the whole distance between these two plates is d, and I let it go. Now, when I let it go from rest. It starts to move, doesn't it? Moves to the left, right? And then it's going to crash into that metal plate, right, where the positive charges are? Okay, so how fast is it going when it crashes into that metal plate? Could you answer that? Let's give it a try here. I'll start here with this idea that do I know the equation for the potential? Oh, absolutely, right? Here it is, right? And then I have from that I have my energy. From that should give me my velocity. So, let's go back to Physics 121 and do conservation of energy. Let's say that the energy initial equals energy final. What I start with is what I end with. Okay, so let's begin. I'll go ahead and say that this electron starts at some point. Now I'll kind of have to readjust what I did before, but it's going to start then at the center of it. I will call that its initial position. It goes flying over and crashes into the metal plate, so that's the final position of it. Fair enough? If I put a grid on here, I should probably choose x equals to 0 somewhere. Will it be okay if I choose this plate 0? All right. So I will call this final spot 0, which means the initial spot is d over 2, right? And so when I come over here and say, let's add all the energies, maybe I'll start with kinetic energy. I set it there and I let it go. Okay, so what's kinetic energy? Yeah, I let it go. And since the kinetic energy is 1/2 mv squared, that would be 0. I let it go. It starts at rest. Okay. What is its electric energy? Electric potential energy. Well, that would be its charge times its electric potential. And the charge I'll put as a Q. Now, of course, remember we called that a negative. And we called it an electron. Don't we know the charge of an electron? I'll ask it later when I fill it in, but that's what that means. And then how do I get that electric potential? Well, isn't that what I just did here? Isn't the electric potential negative sigma epsilon its position? All right. So this is negative sigma epsilon position d over 2, right? And just to move it up to the top so maybe you guys could see a little better. Let me go ahead and simplify that equation. I'll put the negative out in front. The three things on the top are the charge I place in the middle, the charge density on the plate, d, the distance between the two plates, and a 2 epsilon naught. So there is what we would call our initial energy. Be careful here. Is this a positive number or a negative number? Yeah, I think I gave you enough information, I hope, to say that this is a positive number. I know it has a negative in front, but what's the charge? Negative. I put an electron there. So eventually when I plug this into my calculator, that's going to be a negative. These will all be positives, and I will have a positive number. Oh, I keep saying I'm going to put in some numbers, and I will. So let me actually give you some numbers. I guess we would need like a D. How far are these plates? Maybe I'll just pretend it's like that one there. Why don't I just say the D is about 10 centimeters. I guess I'll need a sigma eventually. Let's just say I put 1 microcoulomb of charge on these. These, I guess we could measure them and find their area a little better, but let me just do a rough estimation here. This probably is a 10 centimeters or something. I'll just call it a square. So a tenth by a tenth, that's like 100th of a square meter. So again, just to have some numbers to work with, maybe I'll put 1 microcoulomb spread out on because this drawing is a square, maybe I'll put a tenth of a meter by a tenth of a meter. That's the kind of numbers I get. I hope those are reasonable. I'm fearful that I might not have reasonable numbers here, and if we do, then this thing can go really fast. Electrons are really light and they can go really fast. And for those of you who've already gone through Physics 123, you know something about things that go really fast. Yeah, what happens as we get close to the speed of light? Would we use 1/2 mv squared? No. Okay, so the other half of you who haven't gone through Physics 123, I don't want to get into that. So I'm hoping I picked a small enough set of numbers here that we won't be going faster than the speed of light or some ridiculous thing here. So if we do, forgive me. But again, that's not the point here. The point here is that is the energy, right? I can use the principle of conservation of energy and get the answer to the speed. I get that from this new idea of potential. That's what I'm after. All right, well, let me do the other side of the equation. Okay? So this is the initial energy. Let's look at the final energy now. All right, so now the electron has moved all the way over. It's crashed into the metal plate. Let's start with the kinetic energy. And momentarily before it crashes, isn't it moving? So I should probably put something like 1/2 mv squared, right? I'll put a little f for final speed if you want. But boy, this thing is probably moving. And like I said, probably moving pretty quickly. I don't know how big my numbers are here, but I wouldn't, be surprised. These electrons are so light in their mass. It doesn't take much to get them close to the speed of light, or near the speed of light. All right. The other one is the potential energy. And that's what I'm trying to teach you. That would be the charge, okay, times the final potential. So as I carry this down one line, it's 1/2 mv final squared plus, okay, now what's the final potential here? Well, that's why I worked out this equation, right? This potential is based upon its position, and its position now is 0. All right, so I have 0 potential. Now let's see if that matches what, 0. Let's see if that matches what I said earlier, right? Didn't we say that what direction does the potential increase? Isn't it that way? And so hasn't the electron gone from this, if I say this right, the electron has gone from a negative potential to 0, right? Hasn't it gone to higher potential? But lower potential energy, right? Isn't this the energy? Isn't this a positive number once we multiply by a negative charge? And yet it ends up at a 0 potential energy, right? So it went to lower potential energies. Right? It went to higher potentials. I can see some of you want to think about that some more. Good. All right. Well, anyway, hopefully you're getting this idea. Okay, I'm adding the energies here. So the other side of this equation then is, of course, 1/2 mv final squared. All right, well now I'm good to go here. Now I can just put in my numbers and see what I come up with. It looks like there's a 2 on each side, so I'll cancel that. And I've got a negative Q, I've got a sigma, I've got a D, I've got an M, I've got an epsilon naught. And then that should be the final speed squared. So let's put in my numbers. I'll start with the charge of the electron. What is the charge of the electron? Yeah, negative 1.602 times 10 to the minus 19 coulombs. What is the charge density? Well, that's why I was messing around over there saying, okay, let me give you some numbers. This is 1 microcoulomb per 0.01 square meters. Right? So there's my charge per area. What's D? Well, it's the distance between them. It looks like I set it up at 10 centimeters. So I will put 0.1 meters. Okay. Then I got the mass, which is our fun number. You haven't forgotten that one, right? What is it? Yeah, there's our 9/11. Right? Scary part about fall. There's our Halloween, October 31st, right? Another scary number about fall, right? Or negative thing, right? That's why we got a negative there. That's why this class is so negative in your mind, you know, right? Everything happens here in the fall, so all this kind of fits together. So good fall numbers, Halloween, 9/11. Okay, so there's the mass of the electron. Oh, what is the permeability of free space? Times 10 to the 12 units? Okay, so Newton meters squared, Coulomb squared, right? Because it's the reciprocal of Coulomb's constant, right? All right, and that's supposed to come out to my velocity squared. So let's see what that comes out, both in the numbers and the units. I thought it would be worthwhile, since our units got pretty complicated here, to make sure we kind of look at our units and see how they play out here. But as I put in my numbers, you'll see this negative and this negative make the positive. So there's my positive number. That first number, 1.602 times 10 to the negative 19, goes here. Then times this number in the top, which is 1 times 10 to the negative 6, dividing it by 0.01, multiplying it by 0.1. And so there's my numerator. I will take my numerator and divide it by 9.11 times 10 to the negative 31. I will take that one and divide it yet again by the 8.85 times 10 to the negative 12. And, this is pretty fast. Let's see what it comes out to be. This is 2 times 10 to the 17. Ooh. I got too much on there. And so if I take the square root, I get, in scientific notation, 4.45 times 10 to the 8th. All right, bummer. I got too much charge on here. This would be inappropriate to use 1/2 mv squared. But skipping over that for a moment, and maybe reducing my charge here or the area of my plate or something, this electron would be going pretty fast. And hopefully in the problems you have, we won't give you so much charge that it gets close to the speed of light. So we'll just do the 1/2 mv squared and we'll find the speed of it. Let's check the units. I suppose I could have made a mistake. Doesn't seem like there's that much charge on there. I tried to keep it low, but yeah, 1 microcoulomb is pretty much, oh, that's quite a bit for that size. Yeah. Okay, so with that said, I don't think I made a math mistake, unless you guys out there, anybody else do the numbers? Yeah. Just trust me. You got the same number? Okay. All right. So Other than that is not a very realistic number. You're not going to get that much charge on here, or if you did get that much charge on there, this electron should not be using 1/2 mv squared to get its speed. But let's look at the units here. As you'll hopefully see, I've got a coulomb and a coulomb in the numerator, but a coulomb squared in the denominator. So that's going to go away here. Also, looking a little carefully at this, you will hopefully see that this meters squared, which is in the denominator of the denominator, meaning when I flip it, it's really in the numerator, right? So that would cancel with that. Okay. And so what I am left with then is meters in the numerator here. I am left with kilograms here. This Newton, again, being in the denominator of the denominator, and I flip, ends up there. And so I've got a meter, I've got a Newton, which we know is a kilogram meter per second squared, and then the kilogram. So the kilogram cancels off, and I've got meters squared over seconds squared. Yay! Because then, when I do the next step and take the square root, I get meters per second. So yes, the units work out beautifully. Okay? And of course, never assume that they do. I know a lot of times in the mechanics, our math gets so hard, we just kind of blow the units off to the side. But when we do that, hopefully you're really doing them in your head, right? You're doing them on the side. You know they're going to work out. You're just not writing them down. But they should work out. And sure enough, you see it here. And so I would encourage this, especially some of these new units like voltage that you haven't seen before. It's probably good to work with the units just to kind of learn them. Electric field, newtons per coulomb, those things are new to some of you. But again, hopefully it illustrated my first point. And my point is this. If I know the potential, could I now put a charge there and figure out its speed? And my other point, besides going this direction, potential leads to potential energy, which leads to speed. Couldn't potential lead to field? Let's try that one. Let's clear the conservation of energy off the board. And say, all right, how could I get the electric field? And do you see it up here? Maybe we should run a little math. It's the same math we did in Chapter 8. This is really saying that if you take the potential, and I'm just going to drop the change in potential here for a moment, and take this integral E dot dr, and maybe if you separate it apart into this dot product really means electric field in the x direction dx, right? And electric field in the y direction dy. Isn't that a dot product? Don't the x's multiply together plus the y's multiplied together? And so I want to rearrange this equation. I want this equation to be electric field. How do I get rid of this integral? Yeah, so I have potential equals. And the first integral is the electric field in the x direction. The second integral is the electric field in the y direction. And if I wanted to get rid of this integral, what do? How do I undo an integral? I take a derivative. So I will take the derivative with respect to what? X or y? See, I want to get rid of the x, then I need to take a derivative with respect to x, and that would give me minus the electric field in the x direction. Now, it's kind of a tougher question. Well, what does that do to this one? Well, let me be a little clearer here. Here's what I mean. What I mean is change the potential, or look at change in potential as you move only along the x-axis. Some of you will recognize the symbolism from your math class, maybe more like this, which you might call a partial derivative. And again, here's what we mean is don't change your position any old direction. Change your position only along the x-axis. And so if you were measuring the potential along the x-axis, we say only change in x. Because what does that mean about the y? Y doesn't change. And if Y doesn't change, then when you're taking the derivative of a Y, it doesn't change, so you treat it as a constant, and derivative of a constant is 0. So that's why that one goes away. And so what this says then is the electric field in the x direction is negative the derivative of the potential. And for the same argument, the electric field in the y direction would be the derivative in the y direction. And that fancy symbol here, which I think your book just kind of brushes off and says, look, just take a derivative. And take it with respect to x or y. And if you're taking it with respect to x, didn't treat anything that's a y as a constant. Okay? And so that's really what that means here. Okay? But notice, this is what I was saying. This is the second point of the lecture. Could I get the electric field in the x direction from potential? Yeah, take its derivative. Could I get the electric field in the y direction? Take its derivative. And likewise, had I done this in terms of polar coordinates, wouldn't this be minus an integral of ER dr? And so I could say the electric field in a radial direction would be negative the derivative with respect to r. That is, not worrying about how theta or phi might be changing. I can just take the derivative in the r direction. So that's what I meant in this little diagram when we got started an hour ago, was that, look, if you know the potential, we can get to energy, which we can get to velocity, or if we know the potential, we can get over and take a derivative and get electric field. Okay? So let me use this first one as an example. Let's say we know this, but we don't know the electric field created from this plate. Now, I know we already did, because obviously we did that with Gauss's law. In fact, we used it here to even get this equation. But to illustrate my point, let's pretend we don't know what the electric field is from this configuration. But what we do know is the potential. Could you get the electric field from it? Sure. Let's give it a try. I would come over here and say, could I get the electric field in the x direction? Well, the electric field in the x direction, according to this, would be negative times the derivative with respect to x of the equation for the potential. And I know it. I see it right there. It's negative sigma x. The negative and the negative go away. That makes a positive. The sigma over epsilon, that's a constant. I'll pull it out. The derivative of x is 1. And there it is. Right? Isn't that the electric field in the x direction? Isn't that what we already know from Gauss's law, the last chapter? Okay? And that's what I wanted you to see. If you didn't know it, you could have found it. That's what I meant by this. It will give you a third way to find the electric field. We got Coulomb's law, we got Gauss's law, and now we got the process of potential. Okay? And in fact, no electric field would be complete until you found all the components. So we technically need to do x and y. So that means take the derivative, again, with respect to y of the equation negative sigma over epsilon x. What do you get? Yeah, you get 0. There is no y in there, right? It's a constant in terms of y. Potential doesn't change in terms of y. And so this is 0. And so the electric field can be found. I can get the x component, I get the y component. And that's exactly the field that we have been saying. Okay? And so again, that's this whole idea. Start here, feather down, right? All right, well, let's keep going. Let's keep talking. I'll leave that picture on here. Maybe I'll leave this up here, and now I'll just kind of have to get rid of this one here so we can kind of keep drawing on our picture here. But as I'm looking at this picture here, let me ask you this question. And maybe I'll begin by going all the way back to mechanics again. I'll go back to our potential energy, our gravitational potential energy, right? And so let me take an object. Maybe it's one of these batteries here. I'll take this battery and I'll hold it right here. Now, we learned that it has some gravitational potential energy, right? If I move it down, it has less gravitational potential energy. Fair enough? If I move it up, it has more gravitational potential energy. Is there anywhere I can move it that it would still have the same gravitational potential energy? Oh, over to here? Level? In a plane? Anywhere on this plane? How come? Because it doesn't change? Well, why? Why doesn't it change? Because what? Okay, it's down, so? All right. So, in other words, our definition of work was how much distance did you move in the direction of the force, right? And the force is up and down. And as I move this way, how much distance did I move up and down? None, right? And so that's why back in our mechanics, we said, and I don't think we used this word, but this is the word I want to throw out there. For 2/3 of you already heard it because we did it in the lab, but for the other third of you today, you're going to do it in the lab. What would we call this surface? Yeah, it all has the same energy. So we call this an equipotential. Okay? The same amount of energy everywhere on here. How would I recognize that this is the same energy and this is not? Perpendicular to what? The force, right? In other words, the whole reason that going this direction is an increase in potential energy is because my movement is in part a component of the force of gravity. If I have any movement that is slightly up, then don't I have a slight motion in the direction of the force? So the only way I can stay at the same energy level, the only way I can have the same equipotential is what? Where do I have to move? It's perpendicular, right? And so I've got to be perpendicular to the force. Fair enough? Well, we're going to do the same thing here. We didn't really do that much discussion when it came to our mechanics here. But what if I were to come over to here and maybe grab a different color and ask, okay, now back to this picture here. This picture here, we've got this electric field here. We realize that as we move along the x-axis, we change the potential. Where would be the equipotentials? What would they look like up here? Right. If I were to draw a line, or I guess I should say a surface, because it's really back, a surface that is parallel to these plates. And so you could see it a little better. That's why I thought I would bring out these parallel plates here and say, look, this equipotential would be like the surface of this piece of paper. If I were to put the piece of paper here, everywhere along in this piece of paper, or maybe I should get a bigger piece of paper. Still someone's homework here, okay? Everywhere on that piece of paper has the same potential. Because it's at the same position on the x-axis. If you look at this equation, everything that's at the same x position would have the same value of potential. It's not until you move in the x direction do you change your potential. Fair enough? And so that's my equipotential. And so I can draw another equipotential, another equipotential, another equipotential. And for those of you who did the lab, and those of you who are about to do the lab, we did something like this. We set it up so that this plate over here had a potential of roughly 10, and this one was our 0. So there was a change in potential from high to low, right? A decrease in potential. Notice the decrease is in the direction of the field on the x-axis. Okay? But if I were to be somewhere in the middle here, and it may be exactly in the middle, I would expect to find a potential of 5, right? Exactly in the middle. As I move a little bit over to here, this line would maybe represent a 6. So there's an equipotential of 5 volts, there's an equipotential of 6 volts, there's an equipotential of 7 volts. This way might be an equipotential of 4. This one's a little closer, so I'll call it an equipotential of 2. Okay? And so these are my equipotentials. So there's maybe a new word for you, or at least 2/3 of you heard it there in lab. But again, look closely at this. What is the relationship between the equipotential surfaces and the electric field lines? Aren't they perpendicular? And those of you who are about to do the lab, and those of you who did the lab was to find the electric field. How did we find the electric field in lab, for those of you who did it yesterday? What did we do first? We found the equipotentials. And those of you who are going to do it this afternoon, that's what I'll do. I will get you a meter. And I'll say, here's a meter that measures electric potential. We'll call it a voltmeter. And you will find all the equipotentials. And you will draw them, just like this. You will say, okay, let's find all the places in space that there is a 5. And you'll draw them in our little drawing apparatus, which you got to see it for it to make any sense. And so, little drawing apparatus. And we can put all the points that are 5, and all the points that are 6, and all the points that are 7. And then once we know the equipotentials, we should be able then to draw the electric field, because we know they've got to be perpendicular. Okay? Is a key step, that they got to be perpendicular. You know they're perpendicular. For those of you who might soon have more mathematics, or already have, as some of you have, complex numbers can sometimes be a real helpful when you do electricity and magnetism. It's beyond the level of our class, but if you have a complex number, you have a real number and imaginary number, right? And you probably have done a little bit. Have you ever done complex numbers on a grid and you put like the real axis and the imaginary axis? And so isn't the imaginary axis perpendicular to the real axis? So you could write out the equations, and the real part can represent the electric field, and the imaginary part can write the potentials. They're perpendicular to each other. And you can be solving for both at the same time in the same set of equations. Very powerful tool and very useful set of mathematics. And so we won't do that, but maybe I'll hopefully set you up for next year after you have transferred here and you've gone on, as I said before, bigger and better things, and on to greatness, and make lots of money and donate money back. And remember, I like red Ferraris, you know. So that's what you're going to see here as your math skills get better and better. In fact, some of you already have been asking me, because your math skills are beyond the math of this book, and saying, well, couldn't I do this with multivariable integration? Yeah, you could. You could. My fear is, though, if you do, you might miss the beginning physics and not really get the conceptual picture, because you will do it next year. Okay, and so you will use all your multivariable calculus and your complex analysis, and depending on how far your math education goes, which kind of also depends on what field you go into. You guys will start going in your own ways. Electrical people this way, mechanical people this way, scientists this way, engineers that way, you know, and so kind of have a different direction of study now, and you won't be in classes of 200 people. Oh, we're not 200. Sorry, we're only about 109, I think. So, although I don't know, at a big university you still might. So, even though it's upper division, probably not. Probably not. They tend to get smaller there. Well, anyways, I think you've seen my main point. I'll do it again. Okay, I'll do the same point again. Now, let's change it. Instead of looking at what I would call the easiest one, why don't we just look at a point charge? This would be the second easiest one. Good place to start. Let's look at the electric potential. And for that matter, the electric potential energy. From do I want to say electric potential energy yet? Let me hold off on that. Okay, let's just, how about electric potential from a point charge? Because now, that I think, at least I'm hoping, I got the main gist of potential across here. What is potential? What is the unit? Why do we care about it? Once we have it, we could use conservation of energy, or we could take derivative, right? We could either get velocity or we can get electric field. Really, this one is not going to be all that helpful. But what if I know the potential from one point? Why would that be helpful? Because then what happens if I have 2 points? Couldn't I just get the potential from one plus the potential of the other? How about 3? How about 4? How about an infinite? And couldn't I look at any configuration and say it's nothing more than a bunch of point charges and I can just chop it up into little pieces? Know what we did back in chapter 23 when we did Coulomb's law? Yes. And so if we can find the potential from a single point, we can find it for anything, right? And so that's really what's going to happen on your homework. You're going to know it for a point and find it for a rod, find it for a ring, find it for a disc, find it for a cylinder, find it for a cube, find it, right? All kinds of different shapes. And then once you know the potential, you can get the speed or the field. So let's find it from a point. The easiest one, like I said, is really this parallel plate. Second easiest one really is a point. Fortunately, a point's not too hard. If I take a little point charge, and I remember from previous chapters that that point charge does make an electric field. It's radially outward if it's a positive charge. It's radially inward if it's a negative charge. Let me just draw a positive, but the same thing in reverse would be true if it was a negative charge here. But if I take this idea right here, and I say, what is the equation then for the potential from a point charge? Okay, I think I can solve it. I can say, all right, the change in potential equals negative integral from beginning to end, initial to final, of E dot dr. Let me just pick a beginning point. Where is my initial point? Maybe I'll start here and say, okay, let's go here. Let's move out to there. Initial to final. All right, so here's my integral. Initial, final. I'll start there. Do you know the electric field from a point? Oh, absolutely, right? That's how this whole class got started, way back there in Coulomb's law. Electric field was what? We said it was Coulomb's constant. Again, let me change it here to 1 over 4 pi epsilon naught. I like that a little bit better. It is the charge that you place there, and then it is an r squared. Now that's just its magnitude. What direction is it? Isn't it radial? Okay, in this case it looks like an x-axis. Well, I'll just say it's radially outward, because I could have done it just as well this way, and then you wouldn't call it I hat. So it's radially outward. The reason I say that is because when I take this dot product, I should probably put cosine of the angle between the direction of the electric field and the direction that I'm kind of moving through space to find out this equation. Well, I'm purposely setting it up when I think is probably the easiest way to do it is, what is that angle? Do you see it here? 0, right? That's 0 degrees. And what's cosine of 0 degrees? 1. Okay. So what I have then is an integral, negative, initial to final, 1 over 4 pi epsilon naught, q, and this is the big one, dr over r squared. Because this negative, the q, the 1 over 4 pi epsilon naught, all pulls out in front, and I get an integral of dr over r squared, evaluated from some initial to some final. And so there is exactly the same thing we did here. Here, though, was kind of a simpler integral. Fortunately, this one isn't too hard either. I think you can do this integral. What does this integral become? Isn't that a negative 1 over r evaluated from some initial spot to some final spot? And then fortunately our two negatives cancel off, making a positive, and I get q over 4 pi epsilon naught. I guess I might write this then as a 1 over r final, minus 1 over R initial. And since this is supposed to be equal to the change in potential, I would write this as final potential minus initial potential. So if I kind of look at the first term as the final, it of course is Q over 4 pi epsilon naught R. And the initial potential is Q, final, over 4 pi epsilon naught R initial. Or just generalize it, the equation for the potential from a point charge becomes 1 over 4 pi epsilon Q over R. Right? And maybe that deserves a second box, and a third box, and a fourth box. Because here's the strategy. We know the potential from a single point. So now, could we get it from a ring? Couldn't we take a ring and think of it as a bunch of points and add together? And so we're about to do that. Could I get the potential from a disk? Yeah. And I can do that. And I will do that. Right? And why would I care about the potential? Oh, well, once I have the potential, if there's another charge around and it was released, I can get the potential energy, and from conservation of energy, I can get its velocity. Or, if I know the potential, I can take its derivative and get its electric field. Right? And so again, I've said that many times, but that's what we are after here. Okay? And so there is the potential. Now, look at this equation. What do the equipotentials look like? Here's my green again, equipotentials. What would they look like? Right, the equipotentials would be every place they have the same potential. Looking at the math, that would be every place that has the same radius. Those are spheres around it, right? And notice the spheres are perpendicular to the electric field. That's, again, what I want you to see. So here is a dotted line representing the equipotential. Here is a dotted line representing the equipotentials. And so the equipotentials are perpendicular to the field, right? If you know one, you know the other. And so here's the field, and I got the equipotentials. Here's the field, I got the equipotentials. Okay? Doesn't surprise me that they're perpendicular to each other. That's our dot product. Okay? All right, so like I said, what I wanted to show you first here is what is the electric potential from a point charge. Because let's illustrate the same thing you've already seen. Let's do this. Let me kind of keep this here on the board. Let me kind of clear this one out here and say, all right, let's say that this little positive charge right here, okay, is kind of stationary, if you will. Maybe it's a bunch of charge on the top of this faucet. It can't move. But then I put a proton 10 centimeters away from this positive charge and let it go. What's its maximum speed? Where is its maximum speed? What will happen here? How am I going to solve this one? Well, I've got a bunch of charges here, and I put a proton. Proton's what? Positive. Which way is it going to get pushed? Away. And so it's going to move out to here. And keep going to go faster and faster. And even when it's way out here, isn't it still being pushed away? Now, I would agree it's not by much, because it's pretty far, but it's still pushed away. So isn't it still going to go faster and faster? So where would you say it's going its fastest? At infinity, right? You're saying the farther and farther and farther away this thing gets, the faster and faster it goes. Okay? Now, granted, after it goes, 10, 20 meters, the change in speed from 10 meters to a million, billion, trillion meters is probably not much. But calculating infinities are really nice at times, and this is going to be one case of that. And so we'll tell you about, okay, I'm really saying you need to think about where is it going its fastest. And in this case, it's really far away. So let's treat it like that. And let's use our conservation of energy, the same thing I was showing you before, and see if we can find the speed of this. You see okay? All right, so I will come along here and say, all right, let's put that little proton here. All right? So I will put a little p with a plus right there. Did I say how far to set it? Did I say 10 centimeters again? All right, so let's start initially at 10 centimeters away. I'll just say the charge is Q. That way I won't have to worry about it going faster than the speed of light. I'll put in every other number except for that number, and then we'll make sure if we wanted to finish it, we would finish it with a number that is small enough that it would still make sense to use 1/2 mv squared. But I also thought I'd pick a proton this time for a couple reasons. One, I wanted to go repelling, and I already told you that was a positive charge. But the other one, since it has a lot more mass, it's harder to get it to the speed of light, and usually the protons don't have that problem of, you know, that equation I just did where it was so easy to get the electron close to the speed of light. Protons, they're still not that heavy, but I just don't want to get too much charge there. All right, but I think I'll still illustrate my point here. My point is use conservation of energy. Use this new idea of potential to find potential energy. Then the principle of conservation of energy to find speed. So initial. Well, initial. Again, initial is I place it here at rest. So what's the initial kinetic energy? 0. What's the initial electric potential energy? Right, it is the charge I am going to place there. How do you want me to symbolize the charge I place here? I don't want you to confuse it with that one. Should I put like a Q1 and Q2? That'd be better? Okay, why don't I do a Q1 and a Q2? So the charge I place here on the sink, on the faucet, I'll call Q1. And then this proton then is going to be charge number 2, which we do know that charge, so we can put that into our equation in a minute here. But I'll just symbolize it by saying I am going to put a charge of Q2 at a point which I will say is the initial potential. And that potential is created by charge number 1. Fair enough? Because here's why it's important here. As I make this next step, here is Q2. But how do I calculate the potential at this point created by that charge? Well, that's what this equation is. And so the potential at that point would be 1 over 4 pi epsilon naught Q1 over the distance away, which is 1/10 of a meter, 10 centimeters. Okay? And so if you look closely at this, you are, of course, really saying that potential energy between these two is 1 over 4 pi epsilon naught, charge of one of them times the charge of the second over r, right? See, one of the charges comes from the fact that it goes here, which is creating the potential. The second charge comes from the fact that the energy is the charge you placed there in the vicinity of the potential created by the other charge. And so we end up with both of them. Now I'll finish the problem, but this is a great time to maybe come over here on the board and write this equation. This equation. This equation. And that equation. Boy, they sure look awful closely alike. Are they all the same? Yeah. So you're not going to confuse them, right? And you've seen all these in these first 3 weeks. So let's review. What's this one? This is the electric force between them. We saw that on the first day. What's this one? Yeah, this is the electric field created from a point charge. I think we saw that on the second day. It was still the first chapter, but there was the electric field. And now,
That's when it's outside of the electric field outside.
yeah, this is the electric field from a point. So this is the force between 2 points. This is the electric field created from a point. So yeah, we got to be outside of a point. What's this one? Yeah, this is the one I just have worked out for you, and I'm trying to show you. This is the electric potential created from a point. And then this one is what? Yeah, this is the one I just came across here when I took the electric potential and multiplied it by the other charge. This is the electric potential energy between those two. Force, field, potential, electric potential, energy. Energy. Potential energy, right? Don't mix them. All right? So, very, very close, obviously. Okay? And let me come back here and then keep working with this. So, this would be my starting point, if you will. I put the proton 10 centimeters away, I let it go. So, 0 speed, there's the energy associated with that configuration. Okay? And I think you can also see in the equation that as the proton moves away, doesn't the distance between them get greater and greater? And so what happens to the electric potential energy? As R gets bigger and bigger, what's happening to the energy? Smaller and smaller and smaller. So this is going to lower and lower energies, right? It's moving out, as it should be. When you release something, it always wants to go to that lower energy, as we talked about, lower energy. So there it goes, off in that direction, because that's lower energy. If it went that way, it'd be higher energy. It doesn't like that. You can only go that way if you force it. It wants to go towards the lower energy. So the other side of this equation says that, okay, after it has moved a long distance away, it's going to have some kinetic energy, 1/2 mv squared. Right? How much potential energy does it have out there? Yeah, and it's really how much potential does it have. We still have the same charge, but what happens to its final potential, electric potential? Yeah, R gets bigger and bigger and bigger. R goes to infinity. When R goes to infinity, what's the potential out there? 0. And so this just reduces to 1/2 mv squared plus 0. Sure. Okay. And now we can put in our numbers. As I said, I do know the charge of the proton. What's the charge of the proton? Yeah, same as the electron. Just got a positive. As I said earlier, I deliberately not going to try to even guess the charge then of the one I placed there in fear that we'll go faster than the speed of light. So I'll just put a Q1 there. The other numbers, the 4 pi you know, the epsilon you know, what is it again? Yeah, Newton meters squared, Coulomb squared. The distance we already did, 1/10 of a meter. The other side of the equation gets to the mass. So we need the mass of the proton. I wish it was as easy as the electron one. It's not, but it's there in the front cover. 1.67 times 10 to the minus 27. This is probably not a good way to remember it, but it's how I remember it. I know the electron. And let's see, I guess I've been married for 23 years, and I was in graduate school and we were getting married and got a wedding ring. We went down, we got it appraised to get it insured. And I came back with a number, 1836. I was like, that's the ratio of the mass of the proton to the electron. Never tell your fiance that. But I haven't forgotten that if you take the mass of the electron and you multiply by 1836, which I guess is what the ring's also insured for, you would get that number, which is the mass mass of the proton. So that's how I remember it, but it probably doesn't work as well. So putting this into here, calculating it, we could get the velocity of this proton as it goes further and further out. Okay? And so again, illustrating our conservation of energy. Also illustrating is, couldn't I also use potential to find electric field? Sure. How would I find the electric field from a point charge? Now, I know we already know it, but let's pretend we didn't know it. If we didn't know it, but we knew this equation, could I get it? Yes. How do I get it? It is negative the derivative with respect to r of the potential. So negative, let's take the derivative. And so I got a 1 over 4 pi epsilon naught. I've got my charge. I got my r there. And so the charge comes out in front. The 4 pi epsilon naught comes out in front. And when I take the derivative of 1 over r, together with this negative, I get a negative 1 over r squared. Putting them all together in the form we're used to seeing, I do get the equation for the electric field from a point charge. Okay? And so again, that's the whole point of what are you going to use electric potential for. And it really is a way of giving us our energy. In fact, some of you have kind of just skipped all this fundamental stuff already, and you're in the circuits class, and you're talking about potential, and you're talking about currents, and you're already saying, look, it's pushing the current, and this voltage pushes this much current, and that's what happens. And you went right to Ohm's law. I'm not sure how far you are in your circuits classes. But what you're doing is you're learning that word potential. You're learning that it represents how much energy. You're learning that it's a force from an electric field that's pushing the electrons, that is making the current, that is then making the energy that makes the motor in the circuit work, or makes the light in the circuit work, or makes the resistor get hot in the circuit, whatever you guys are working on right now. And we're about to do a lot of those too. Coming up here, we will use all this information and kind of transition a little bit into circuitry here, and we just kind of come out of it from the foundation, if you will, from the the fundamentals here. Where does it all come from? All right, well, I said that the balance of the time that we will spend together is really just doing more and more examples of this, in the sense that we will say, start by finding the potential, and from that you can set up a problem that would give you the speed of these moving charges. And I didn't use the word current, but that's what we're leading to. These moving charges are the currents that are flowing, and so that's where we're eventually headed here, these little charges that get pushed around. So let's elevate it one more step. We went from the parallel plate, we went to the point charge. Could you do this one? Could you tell me the potential along an axis of symmetry for a ring? And again, this is why we were learning that skill back in chapter 23, and actually learning that skill way back when we did center of mass and rotational inertia back in physics 121. We got to break it into little chunks and add it together here. So I'm going to come over here and I'm going to take a ring and say, all right, let's look at a ring. Again, let's just say there's a charge Q on the ring. Now, so I can be consistent with your author, I'm trying to remember what he uses for the radius of a ring. I noticed, seemed like the last chapters, he used A, and I think he still does. So I will go ahead and use A also. So here's my ring. It has radius A. Here is the axis of symmetry. I'll label this as the x-axis, putting the origin then in the center of the ring. And again, these three-dimensional pictures are a little hard to see on the board. A, they're hard to see. B, my drawings are not as detailed or as clean as the ones in the book there. I maybe should turn on the overhead, but since we only have 15 minutes, I go, okay, let me just hold it up here and say, look, this is what I'm after. Could you calculate the potential right here? Some distance x? Which, of course, some distance x could mean here or here or here. And so we get a little formula, right? A little formula for what is the electric potential on here. And my argument is the same as we did before here. That, look, if you set this up and you come out to a point right about there, so that you are a distance x out, you can get the potential there by looking at this ring, and that's why we put that little piece of tape there, by cutting it into little pieces, right? And saying, look, I am going to add up these chunks. So I will go chunk, 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 right? And just separate it into little pieces. And so if I were writing it this way, I would say the total potential is what? Well, I guess it would be the sum, and I'll put a little I there. It would be a sum of the potential from each of the individual pieces. Okay. Now, how do I get the voltage from an individual piece, a small little piece? Well, that's why this was so useful. Okay. What I could say is a little tiny piece really has a small amount of charge, call it dq. And so it would be 1 over 4 pi epsilon dq over r. But to be technically accurate, this has to be a small piece, right? It has to be smaller and smaller. I have to take the limits as what gets small. Yeah, the charge, right? I'm taking a smaller and smaller piece of chunk. The charge is getting smaller as I do that. It's not x that's getting smaller. It's not a that's getting smaller, right? It's not, well, epsilon or pi getting smaller. I mean, that's obvious. But it's a little chunk there. And of course, then that leads into our calculus that this would be an integral of 1 over 4 pi epsilon naught dq over r. Now, at this point, I'm hoping you see one of the things we also saw when we started dealing with energy. What was nice when the question was, find the speed using conservation of energy compared to forces. There was really something nice. I personally think chapter 8 and 7 were a little bit easier than 5 and 6. And a big reason for that is when we were doing forces and net force. And we had to add all the forces together. Weren't they vectors? So not only did you have to worry about the magnitude of the force, but also its direction. And didn't we have to worry about that back when we did chapter 23 with Coulomb's law, the electric field? Wouldn't the electric field have a magnitude and a direction? Did you catch that we do not have magnitude anymore? Did you catch these are all scalars, right? Just like gravitational potential energy was a scalar. And then because we took a dot product, we got a scalar. And it's because it's a scalar, when you start adding energies together, energy is really when you take 3 and 4, and you put 3 and 4 together, you do get 7. But if they're forces, does 3 and 4 always make 7? Now it depends on their direction, right? 3 and 4 in the same direction make 7, but 3 and 4 perpendicular to each other make 5, right? And so how much does 3 and 4 make also depends on the direction. Those integrals, I personally think, the integrals that you already did in chapter 23 are harder than the ones I'm about to do for you. Because that's the magnitude. Any angle to worry about? Any x component? Any cosine or sine of the angle? No. So I'm not going to draw like I did before, a little arrowhead, say this is the electric field from this point, and it cancels with that one. It makes no sense to say it cancels with that one. They don't cancel. They're not vectors. Fair enough? They're scalars. And don't miss that. Because number one, you got to see that to set up the own equation, and you don't want to be talking about components anything. But number two, I suspect that you might find a lot of the problems easier by doing the potential energy and electric potential than you will with the electric fields adding together. Okay? Because adding all those electric fields was, I think, a little bit harder than what we're doing now. Just like when we did Newton's laws in chapter 5, we added all the forces together. And they were vectors. But then we got into chapter 7 and 8, and we were scalars, and we just had to add energies together, just regular numbers. Where 3 and 4 always made 7. It wasn't, well, 3 and 4 sometimes make 7. And sometimes it makes 5. And sometimes it makes 6. And it all depends on the angle. And I got this I hat and J hat components. You don't have that here. So that's the beauty of this. I don't need to draw an arrowhead on here. I couldn't. I shouldn't. It is just a scalar. All right, so now let me do the actual integral. Well, as I add up around that ring, what would you say? How about the 4 pi and the epsilon, they're constants, right? Anything else a constant? The radius is too. We had that same benefit when we did this for the electric field. We said that the way this one's set up and why it makes a good third example, as we went from parallel plates to single point to now a ring, is that what we have is we have this r. You can think of it in terms of Pythagorean's theorem, that if you take the a squared and the x squared and you take its square root, you will get r. And looking at that physical picture here, hopefully you're seeing that as you add up from here to here to here to here to here to here, all the way around the ring, you're always that same distance r away. So I pull it out. And that's why I said this might have looked a little intimidating at first, like it's a hard integral, but it's really not. It pulls out. Because now what's this next step? What's this? Yeah, that's just the total charge on the ring. And so there's my equation for the potential. Yay! And that's what I wanted to illustrate. Could you find the potential from some other thing other than a point? Yes, by adding a bunch of points together. And I get a ring. Now, what would I do with it? All right, well, let's try this for a moment. Let's just say that this ring is positively charged. And not in the short time, not worrying about the numbers, but what if I were to tell you that way over here, many millions of miles away, I have an electron and I let it go. What's its maximum speed? Well, what's going to happen to this little electron? Right, won't it move to lower electric potential energy? Which means it's moving to higher potential. So where is the highest potential according to this equation? Where does this number get the biggest? Where? When x is equal to 0. Now that hopefully doesn't surprise you, because wouldn't that little negative electron be pulled in faster and faster and faster as it's getting to the positive? And so it comes in, and if it was right along the axis, since there's charge and a ring around it, it wouldn't get pulled to the left or the right or up or down. It would go right along the axis, and it would eventually get to the center. And once it passes through the center, then what happens? Now it's going to be pulled back, and I would expect it to slow down. So just looking from the forces point of view, the stuff we already did, I would expect this thing to go the fastest when it is at the center of this ring. But I now also expect that from this equation. This equation tells me that that electron should be going the fastest where the potential is the highest. Because where the potential is the highest, the potential energy is the lowest. Because if the potential energy is the lowest, the kinetic energy should be the highest, right? And so I can then apply, real quickly, my little formula. I'm going to start way, way, way out at infinity. How much kinetic energy do I have when I release it? 0. How much electric potential energy do I have? Well, I guess I have the charge of the electron. Let me just real quickly write that as an E for now. How much potential do I have there? What does this equation say when x is way out there? 0. So in other words, way out there I have 0 total energy. Which sounds kind of funny. How is it going to lose energy? Can it lose energy? Can it go negative? I mean, couldn't we have done this with gravity? Couldn't we have called this height 0? And you put it up here? Or you put it here. How much energy does it have here? 0. So does it go below 0? Yeah. So there's decreasing. So what's going to happen is this thing is going to start with a lot of energy, 0, and go down from there. Okay? And so on this side of the equation, I will have 1/2 mv squared, and I will add that to then the potential energy it will have when it gets at the center of the ring. I will put the charge of the electron, then the potential is 1 over 4 pi epsilon naught. It's the charge on the ring, and when we're at the center, as you already pointed out, my x would be 0, so this would be a. And you'll notice that's a negative number. Move it to the other side. After a little bit of algebra, I will get the speed. What is the speed? What's the second reason for wanting to know the potential? What else could I get? Answer? Yeah, I can get the electric field. So, let's see if I can find the electric field in the x direction and the electric field in the y direction. The x direction would be minus the derivative with respect to x. The y direction would be minus the derivative with respect to y. Let me put them in. I got a 1 over 4 pi epsilon naught, a q over a squared plus x squared to the 1/2. Down here, I have the same one. In fact, maybe I will do this lower one first. What is the derivative of this lower one? 0. So what does that tell me about the electric field? None in the y direction. But again, we knew that from 2 chapters ago. We calculated the electric field from a ring. Let's hope we get the same thing. Okay? To convince you this does work. And one thing we did get is we got that the electric field along the axis was along the axis of symmetry. In other words, it did not have a component along the y-axis or the z-axis. But now that I take this one, I'll put the negative, I'll put the q, I'll put the 4 over 4 pi epsilon, and now I have to take the derivative of this thing. Real quickly, that's a negative 1/2. That's an x squared, a squared to the 3/2. Derivative of the inside is 2x. Negative cancels with negative. Half cancels with 2. And I have a q. I have an x. I have an x squared plus an a squared to the 3/2. And I think when we did it before, we wrote that as Coulomb's constant up there. And so, yes, I got the same thing. All right, well, a couple more examples I'll do for you, but I really want to do some in the back of the book. I think you're getting the point, why we care about the potential. Good luck. Work on these weekends. More next week.